Okay, so we're going to try and use all what we've worked out and come back and have a look at some calculations. This is actually something you have to do yourself, basically, do some numerical calculations and match them up. So I'm just going to read off the notes a little bit here, but there's the answer that we found for the delta function potential. So that's scattering data and that's how it evolves. But what we're more interested in, we can't compute for the delta function potential numerically. So we're going to solve for this hat function potential. So it's going to be 0 and 20. So those are the numbers. So we have to calculate these are the two transcendental equations we solve to try and calculate the value of the lambda. And this is the numerical solution of the problem. So this is what, so let's just have a look at what happens. So there it starts out, okay, and it's that hat function. I've smoothed it a little bit, but that's not super important. It just helps in numerics. And then it breaks into these three solitons with heights here. Of the highest one has height around sort of 35, 36 or something like that. This one has height of about 25, and this one has height of about 12. And we should be able to extract those heights out of the scattering data. That's the important thing to do. So, because we know that from what we worked out previously, we know that the amplitude of the soliton, when we calculate it all, is given by 2 times kn squared. So we want to work out, so I know that the kn, 2 times kn squared here, say 35. So I want kn to be the square root of half of 35. That's what I should get when I solve this transcendental equation. So that's the thing to try and work out. Okay, so I'm going to go through this kind of quickly, but the equation we want to solve is tan kappa is equal to k over kappa, or tan kappa is minus k over kappa. This gives us the first, this gives us the second, this gives us the third. They appear in that order. And then kappa is given by b minus kappa squared. So we've got to solve that numerically, and we've got to try and work out the solution to that problem. All right, so there's our equation. Tan kappa is equal to k over kappa, and k is the square root of b minus k squared. And in our case here, b is equal to 20. Okay, so we're going to have, so k can go from 0 up to the square root of 20. So we go 0, comma, the square root of 20. That's what we're allowed for k. And kappa is equal to the square root of 20 minus k squared. All right, brilliant. Okay, didn't like that. What's the what have I done wrong here? Minus and then it equals. Great. Okay, so now I'm just going to plot, get us started here, tan of k, kappa. I'm going to go k, comma, tan of, might be easier to go kappa, let's go to k, comma, tan of kappa. All right. Okay, so let's plot this up here. So we're going to plot, we're trying to solve tan k equals k over kappa, so we're plotting tan k and k divided by kappa. You can do this a lot better than I'm going to do it. I'm just going to do this very roughly for you. Okay, so we get two solutions. You've got to be slightly careful here because this vertical line here is just the tan crossing, you know, the asymptote. So the computer stops here, it's going down to infinity, and it comes down here. This is not, so the computer just draws a line here. So this is not really a 0. But there's two solutions. One's here and one's here. So let's try and work out, just roughly guess what these solutions are. So one of them there is 4.291. So we've got, and we'll call it K3 is 4.299. I don't get too many decimal places here because that would be stupid. I just read it off a graph. And this is the K0 here. This one here is about what? 2.48. And that's K1. And then we've got the odd solution to find as well. right? We only found the even one. We're going to get 2 here. There's 3 solutions. There's 3 solitons, right? But there's got to be 3 solutions. So we're going to do and find the odd one, which will be K3, and we go. Now we put a minus here. Okay. And we should see there is only one solution. And it's this one here. Ignore what goes on here. Everything goes back to 0. So it's this point here. So it's 3.97. K2 is 3.97. So, brilliant. We've worked all those out. So what should happen magically is the amplitude of the wave from our soliton theory, that one that we did with that example calculation before, we calculated, we carefully manipulated that thing so it looked like a soliton. We found that the amplitude is 2kn squared. And we can see in this picture what the amplitudes are. So if we take K3, 2 times K3 squared, we should obtain something between around 36.8. Brilliant. Okay, theory is working. If we do 2 times K2 squared, we're going to get the amplitude of the second one, 31. Doesn't look quite right, does it? Okay, so maybe K2 I've got a bit, it's quite sensitive how I read it off the graph. Okay, so we'll just put that down to numerical error, and then K1 squared is 12. Okay, it just seems about that. That's believable here, okay? Sorry, it just worked out I did something stupid. Okay, which is quite fun. So this one is wrong, 31 is wrong, okay? The computer's, because these other ones were too accurate for this to be wrong. I've seen numerical error. Rubbish. It's the equation for the odd one is tan kappa is minus kappa over k. So let's find that odd one again, fix that problem up. Right? So it's not k divided by kappa, it's minus kappa over k. Bad mistake. If we plot that, what do we get? Let's have a look at it. Okay, what's that? There's the 0 there. So x is 3.70. K2 should actually be 3.70. And then if we go 2K2 squared, we get 27, which is much closer, okay? Right on the money again. All right, brilliant. Okay, so you can check it all out. So it is kind of amazing. We're sort of finishing there. I know that we go back to this stuff here. The numerical solution of this is calculated by the method that we outlined. We can calculate for the hat potential solutions of the linear Schrodinger equation, and that gives us the amplitude of the solitons. And of course the amplitude of the solitons also gives us the width of the soliton and the speed of the soliton. They're all related to each other. Okay, by that formula. We've derived that a very nasty expression through this integral equation to obtain that. So your job in the assignment is to try and do some calculations, numerically solve it, and solve the linear Schrodinger equation, find the eigenfunctions and compare them all.